Hello. Thanks a lot for coming. We're going to talk about ray tracing in Unreal Engine 423 today. My name is Juan Cañada. I'm part of the ray tracing team at Epic. So, as I said, today we're going to talk about the status of things in ray tracing in UE4. I will start explaining what we have done so far, the challenges we faced, and then I'll continue showing what is new in 423. And after that, Patrick Kelly will give you a more in-depth information about the ray tracing state in 423 and what are the next steps. So surely you remember that last year at GDC, we presented the Star Wars movie Reflections in collaboration with NVIDIA and ILMX Labs. And the goal of that project was to show real-time ray tracing for the first time. And we were pretty happy with the result, but that was just the beginning. A few months later, last SIGGRAPH, also in collaboration with NVIDIA, we released the trailer, the movie, The Speed of Light, that shows more complex ray tracing effects than the previous one. And with all the lessons we learned with those two prototypes, we wrote the ray tracing technology that we released in 422. And to showcase that, we made this new movie, Troll. We are going to watch it again, just in case you have not seen it. Thank you. Probably you had already seen that. It's always nice to see people like it. So the goal of the movie Troll was not just to showcase ray tracing, because this is what we did with the previous one, but to explore how far we could go in terms of real-time digital content creation, how we could create a cinematographic piece where we mix ray tracing with other fundamental parts of the UE4 pipeline, like Niagara effects, digital humans, the Alembic pipeline, the sequencer, and to see how we could interact with other components of UE4, so people could actually use that in production. There was another goal, another very important goal of this movie, which was to use 422 technology. It was not anymore just prototype code that you could not access to. It was just the same code that you have in GitHub, the UE422 code. We wanted to make it accessible to anyone. So there was no more secret sauce here, but just the UE4 that you guys have access to. So I'd like to explain you what happened from the first prototypes to Troll and to 422. Let's dive into details. Let's just start with some numbers, doing a comparison between those demos. Troll is an order of magnitude more complex than our previous ray tracing demos in pretty much any aspect. It has more geometry, more lights, the light transport, it's more complex, there is way more effects and components. The render time is the same. It's still running at 24 frames per second, which means that we improve the performance of the ray tracing technology by an order of magnitude in 1 year. And I'll explain you how and what challenge we faced. So our technology is much faster now than a year ago. And also a year ago, the Star Wars movie was running into this super high-end machine that was almost $100,000 or something like that. Troll runs in a 2080 Ti, which is a medium-grade GPU. It's like something like $1,000. So when we say that we wanted to make a movie that's accessible for everyone, we were also meaning that we wanted to do something that people could actually run on their machines without having to spend a lot of money. So, well, that's not just that we did a good job. It's also that NVIDIA is doing an awesome work in terms of how their hardware is evolving. So kudos to them. So a few more details on how we went from those prototypes to 422. The ray tracing implementation, the one that we have in 422, is built on top of a major refactoring of the rendering pipeline, which has many aspects. There is a talk from last GDC that I think the video is available if you want details. But one of the components of that refactoring that was more critical for us was the transition from immediate mode to retain mode, which means that now the rendering engine doesn't recompute everything on every frame, but it just has a smart way of caching things in a way that we just recompute what we need. That is very important for ray tracing because by the nature of the ray tracing algorithm, a ray can travel anywhere in the scene, so you need access to all the geometry in the scene, all the materials, and if you want to put all that information on the GPU at every frame and you have to move all the data, well, you will not get the performance that we get after this refactoring. Well, that together with other major optimizations made it possible that we reach the performance that Troll has. And after that, what we have done from 422 to 423 is to make that technology more stable, to keep working on performance, and to add new features that were missing in 422. Let's look into what we have been working at in the last month since we released 422 till today. Stability was the #1 goal of 423. Our ray tracing implementation is built on top of DXR. DXR, as you might know, it's a new API, well, it's a new framework. It's a lot of things, but it's a system developed by Microsoft and NVIDIA for ray tracing on top of DirectX. That is a new technology, which means that it has new drivers, it has a lot of new code, and that path, it's very new. So a lot of the challenges we had when implemented ray tracing were actually NVIDIA and Microsoft, they were working on the API at the same time. So that was pretty challenging. We were not working on top of a very major technology, but we were working on top of something new. And it took time to make things stable. Also, as I just mentioned, we refactored the whole rendering pipeline, and it also took time to keep things stable enough to actually say that the ray tracing technology is production ready. Also, performance has been improved at many levels in 423. We have added significant improvements in the way we create the ray tracing pipeline step objects, the resources. We have improved the performance on many ray tracing passes, like SkyPass, the ray tracing global illumination. Well, Patrick will give you more details on that. And we have also improved the denoiser system, which, as you surely know, denoiser plays a critical role in in ray tracing, in real-time ray tracing, because we have a very low budget for tracing rays. We trace very few rays per pixel. So denoisers they are a fundamental component of ray tracing. And we also work in new features, as you will see in the next slide, which is a brief summary on what we have done in the last month in terms of features. So we have implemented several new low-level features, that intersection shaders. Intersection shaders will allow you, if you are game developers or you are familiar with the UE4 code, to create your own, to support your own primitive types. So you can define your own ray primitive intersection and give it to Unreal, and you will be able to render complex geometries like hair or volumes or fractals or whatever you have a ray primitive equation. Apart from that, we are working on multi-GPU support. The first step in 423 is to provide low-level multi-GPU support, which means that you, as developers, can decide which GPU will render a certain ray tracing pass, and you can also manage resources in the GPUs as you wish. This is different to have a vanilla multi-GPU implementation, where you just plug your GPUs and everything goes faster. That is more challenging, and that is something we are working at right now. Hopefully you'll see some progress in 424 or so. Geometry types are one of the main highlights of 423. We are happy to say that now we support almost everything that the raster pipeline supports. The main highlights there are landscape support and support for instances and hierarchical instances. And we also support now world position offset for skeletal meshes, which is a major change. Lots of existing pipelines use world position offset a lot, which means that we do a lot of geometry conversion and geometry magic in the vertex shader. That is very challenging for ray tracing, because ray tracing needs all the geometry in a very early stage, so we can feed the acceleration structures, and you can actually trace rays and intersect those geometry. So if in your pipeline you have a lot of geometry that is changed in vertex shaders, well, that is a major challenge for ray tracing in general. And this is a very active area of development, and we are happy to say that we support world position offset on certain things now, like skeletal meshes and also landscape. We will try to support world position offset also on hierarchical instances soon. That is an open problem in computer graphics. How would you ray trace a forest with thousands of trees, with all these leaves moving? This is a problem that is a bit easier in the raster path, but for ray tracing, that's an open problem. If you have attended the open problem sessions on ray tracing, this is one of the major challenges. And we have ideas to approach that. Well, this is just a summary. You can see that there's some performance optimizations. Patrick will talk about that, and some improvements on light transport. There's better clear code model, more complex effects, a lot of improvements on translucency, and so on. 423 is going to be released in a few weeks. There is no exact date yet, but Preview 4 is already available if you want to download it. I think Preview 5 will probably release next week. There will be a release candidate after that, and probably in about a month, you will have the final 423 version. I repeat, this is just a summary. I encourage you to go to the official release notes if you want more details on what is new here. And before I finish my part, I like to talk about what has been the adoption of ray tracing and UE4 users. And well, we are happy to say that the reception from users has been very positive. People are very happy. They have been using that from day one. Despite this is an early access technology, we were a bit scared with that. Like, please don't use it in production yet, or do that knowing that this is early access. people really didn't care too much. So they just used that in production from day one because they loved the results. And that was pretty challenging. But on the other hand, that was a great stress test. That was a great way of getting ray tracing ready for production as soon as possible. There is an overwhelming amount of work done with ray tracing in Fortnite 2. You can check YouTube and Vimeo, and it's full of videos. We cannot keep track of everything that is happening with ray tracing in Unreal now. And it's also interesting to point out that there's been the adoption internally at Epic has been great too. Many teams started using ray tracing from day one. The Fortnite Cinematics team, as I'll show you now, and other special projects and demos, they all want to use ray tracing and have adopted that as a fundamental component of their pipelines. The Fortnite Cinematics team adopted ray tracing very quickly, and they have been using that since then. They say that they get better and faster results. The pipeline, the lighting pipeline is more intuitive, more predictable, and they're having more fun. Because when you can work with cinematographic tools and area lights and things that are like a better metaphor of how you will lead things in real life, well, things are more fun and more predictable, and they're very happy about that. So, and they get cinematographic results at 24 frames per second, which is amazing. So to finish my part, I'll show you the first trailer that the Fortnite Cinematics team did using ray tracing. There are more. There is actually one released today. We didn't have the time to put that in our slides, I think, but I encourage you to see that. And well, this is not photoreal as the previous videos that you have seen, but also shows nicely how ray tracing can be used for other purposes. Let's watch it. The greatest thing of that trailer is that those guys just dropped the technology and produced results in very few days, or even in very few hours. It's also an amazing stress test for us, because as you can imagine, Fortnite people are always trying to meet deadlines, and they are pushing us to make ray tracing ready for production. Which is great. So that concludes my part, and now Patrick will give you a more in-depth session with details on all these things. I hope you like that. Thank you. Patrick.
Thanks a lot, Juan. Yeah, my name is Patrick Kelly. I'm a senior rendering programmer here at Epic Games, working exclusively on ray tracing. And I'll go ahead and give the technical outline of this portion of the talk. Runs, I guess, bottom up through the stack here. So we have the RHI layer at the very bottom that connects with the DirectX 12 implementation layer. I'll talk a bit about the mesh pipeline and how we use geometry in our system. And then I'll finish up talking about the different rendering passes, how we get pixels on the screen. So here you can see the fundamental types that we use in the RHI layer. There's not many. There's sets of ray tracing geometry, one ray tracing scene, a bunch of ray tracing shaders, and one ray tracing pipeline state object. For a given frame, we're constructing one ray tracing scene. There are many ray tracing geometries, and one object PSO to bind it all together. One of the first fundamental elements is the geometric instance, and the geometric instance is an abstraction of geometry, but joined with a transform so that we can put it in space. I think of this as kind of the natural method for representation of ray tracing geometry. There's ancillary components like user data and visibility masks. The user data is like an arbitrary index that allows us to seek into the structure and grab material data, like all the vertex data that's bound when we do closest hit shading. The visibility mask is a way to carve out ray paths so that some things can be visible for shadows, say, and not for reflections, or vice versa. The ray tracing geometry, so bubbling down one layer, is composed of a vertex buffer and an index buffer. That's basically it. The vertex buffer is just a bunch of positions. So this manifests as triangle data that's inside of our bottom level acceleration structures. The last component, the geometric segments, is like a span of indices inside the index buffer. So really a bottom level acceleration structure might have a bunch of different spans, and the reason for that is to bind different types of material to a subset of one geometry. And the ray tracing scene is the collection of all these instances. And then the shaders, we have a lot of them. These manifest exactly as how specified in DXR. So we have closest hit and any hit shaders. These are the sort of material binding frameworks that allow us to grab vertex data and execute material shading. We have the mist shader and the ray generation shader, which kind of act as a pair as well. The mist shader, of course, says that we didn't hit anything. The ray generation shader is sort of the bulk of the transport algorithm, so whatever we want to implement is done at this level. Two new shaders for 423 is the intersection shader and the callable shader. Juan had already mentioned the function of the intersection shader. The callable shader is meant to be kind of an arbitrary call out so that a shader can call a shader. And this is currently only exposed in the ray generation shader umbrella. While these are implemented right now as sort of internal RHI level constructs, we're not taking advantage of the last two right now inside our ray generation shaders, but we plan to very soon. So as I said earlier, there's one pipeline state object, one RT PSO, that sort of binds everything together. It binds all passes together too for efficiency reasons. So we basically shove everything together for efficiency purposes. I talked about the mist shader. The mist shader is pretty boring in Unreal. It basically just says we miss. It doesn't take action. Other implementations might do something like evaluate environment maps or take some other lookups, but we prefer to handle that exclusively in the ray generation shader. It's sort of up to your discretion how you choose to use it, but that's our method. And lastly, this one doesn't exist in the top level RHI layer, but it's crucial to DXR. So the shader binding table is really the list of things that associate materials to geometry. And we bind hit groups, which is a pair of any hit shader and closest hit shader to a specific element inside the table, which corresponds to some primitive ID. And it's all sort of abstracted away from the user. Instead, we have this function here, set ray tracing hit group, that's sort of your only way into the SBT. And the reason that we do that is that we can leverage some optimizations when we build the SBT, do things like deduplication to kind of take that complexity away from the user and to get some efficiency gains back. Okay, I'm going to jump in now and transition to the mesh pipeline and talk about the geometry that we support. So to kind of talk about the overall pipeline here, since this is where geometry starts to insert in the system, at the beginning of the frame, we gather all of the instances to be assembled into a scene, and we use previously cached static data, if we have it, to build, it's static, so it's unchanged, but we have dynamic data as well that will build dynamic geometry. And we have a virtual function for that, and I'll talk about that in a second. After all of the instances are assembled to be used in a frame, we apply updates. So if we do have dynamic data that just needs to be updated, it can be refit or it can be rebuilt. And then the scene acceleration structure is built on top of all of these lower level acceleration structures. And finally, the ray generation shaders are collected and bound to that RT PSO that I discussed earlier. And that's basically the end of the geometric pipeline. In order to actually run the execution, all of our ray generation passes operate on the G buffer, so we have to run the base pass, and then we're free to do whatever we want. So this is, again, sort of the list of supported geometry that we have in 423. The new features are outlined in blue here. So static meshes, unchanged data. Skeletal meshes are dynamically changed data. The new element now is to respect the world position offset, which is something that internally we needed for some of our Fortnite trailers. Specifically, they were using deformation on the characters itself, and so we needed to respect that value. Geometry cache is what we use and what we used on Troll for the Alembic representation, so animated data that's streamed into the system. And then we have support from, as you saw in Troll, for Niagara particles. And then landscape is brand new, and we needed that for some of our Fortnite Cinematics stuff, and that allows the landscape to shadow itself. Previously, we had to use proxy cards and surfaces to try to fake the effect. And new instanced static mesh and hierarchically instanced static mesh. Okay, in terms of extending the geometry pipeline, this is the arbitrary, or the virtual function that we give to the developer. And it's got to do a few things. It has to provide geometry and geometric instances, and it also has to supply the material bindings that should go with those geometric instances. It's three different requirements. It's a little hard to explain without dumping a lot of code, so I just give you this file here and how we implemented that for dynamic Niagara particles. And there's some special considerations, and we're still kind of back and forth on what the right way to skin the problem is. But at any point with an acceleration structure, you can choose to rebuild or refit. Refit is significantly faster, but rebuilding has much better traversal performance. So there's a natural trade-off there. Of course, the rebuild takes a lot longer, and we have a limited budget of how many things we can rebuild in a given frame. Level of detail is a consideration that we have for static meshes, but we don't have a concept of that in the engine right now for dynamic data, because it's expected that if you provide dynamic data, you can also choose the appropriate level of detail to submit to the system. And then lastly, we have sort of an artistic control, but the ability to hide different elements from shadows, reflections, and GI passes as the user sees fit. And we use that visibility mask that I spoke about earlier to do so. All right, finally, I'll dive into the different render passes, what we support, and talk a bit about some of the changes that we've made between the 423 and 422 release. So this one is virtually unchanged. There's a bit of snippets at the end, but we are treating ray trace shadows as a drop-in replacement for shadow maps. That's the goal. And they generate visibility masks just like shadow maps generate visibility maps. So it really is just a drop-in replacement when we go for the direct lighting integration. The one thing, of course, that ray tracing can provide us that rasterization can't is the ability to do area light shadows, like in this example. And we support virtually all the light types that we have in Unreal. So there's general parity, with the exception of better looking area shadows, of course. We render our shadows at 1 sample per pixel, and then we denoise the result. This is what a raw image looks like. And this is what a denoised image looks like with the same budget. So it's doing a really good job, and just for reference, I'll give you the 64 sample per pixel. It's not converged, but you can see that it's quite close. And it is sort of linear in time here, so this render took 64x the original render. Move on and talk a bit about ambient occlusion. It's also meant to be a drop-in replacement for the screen-spaced ambient occlusion. The way that this algorithm works is by operating on the G buffer and casting rays in a cosine hemispherical distribution. It records the hit and miss ratio of whether it got out into the environment or if it was occluded by a source. Very, very standard AO technique, but done in world space instead of screen space. And just to give an example of sort of the benefits of the ray tracing one, here's a screen space ambient occlusion image, and here is the ray traced ambient occlusion image. You can see that there's a lot more localized occlusion that screen space can't detect because it just doesn't have the proper amount of information that the global rays do. And of course, this is the noisy image at 1 sample per pixel, and this is the denoised image at 1 sample per pixel. In terms of changes from 422 to 423, there's really only one, and we allow the optional respect of the alpha mask parameter. And this can be used just to give kind of a concrete example. Leaf cards that are texture mapped, this would allow you to respect the bounds of the footprint and the texture. But it's actually not a great idea, and it comes with a heavy constraint. And it's because in the middle of our trace, we have to employ a texture fetch, and that really slows things down. So when we're kind of approached with this problem from other people, we tend to say, well, you should just model the geometry explicitly in the leaves, because the BVH can basically handle the complexity, and the traversal unit is so much faster than executing texture fetches. So this kind of deviates a bit from the rasterization world. Anyway, it's available, and use at your own discretion. To go on further, talking about the reflections pass, this is the first example that uses actual material evaluation, the closest hit shader. And we do this by operating again on the G buffer, and we respect the roughness parameter of the material and cast a GGX array according to the GGX distribution and the reflected direction. We hit a secondary surface, and then we perform direct lighting on that surface. We also have the ability to cast recursive rays, which would give multi-bounce reflections, and that's very expensive, but we can do it. Here is an example of screen space reflections from our troll demo, and here's an example of the ray traced reflections. And once again, it's the same sort of property that the SSAO versus RTAO example had, where SSR is just missing occlusion, or it's missing information that ray tracing can pick up. I'll go back and forth just so you can see again. It's a staggering difference in this example. This is an example of the multi-bounce reflection. And it looks nice, and it's expensive, so it comes with a cost. I'll move on and talk a bit about translucency. Translucency is subtly different from reflection, but not too dissimilar. So our G buffer stores fully opaque materials, and we rely on tracing from the camera to resolve any of the objects that might be partially transparent. And so we trace a ray from the G buffer. We hit a surface. We also have a Fresnel term, and we can decide whether we want to reflect or refract at the point of incidence. Typically, we do both. And while I say refraction, and I got a comment on YouTube about it, so I guess I should clarify it, we usually use an IOR of 1. And it's cheating, but it is ridiculously fast. And refracting in an actual translucent ray is possible, but it's very noisy, and it incurs an actual secondary trace, which is expensive. And in a lot of cases, the refraction isn't noticeable, like in this example here of planar glass. So really, translucency is providing transparency from the point of view of visualizing what's behind it, but also providing a reflection of the environment. Okay, I'm going to finish up talking about some of the other types of integrators, the skylight and global illumination integrators in conjunction. So to give kind of a brief explanation, the skylight operates pass in a similar way as the RTAO pass does, except when it escapes the environment, it records the environment contribution, it integrates those values and provides a result. Now this example is using multiple importance sampling because the skylight, it actually embeds the sun. There is no directional light in this scene. And it does this by employing something called hierarchical sample warping to narrow down and hone in on a piece of the environment map that's important to sample. And if we add GI to it, we can get a bounce light direct from sunlight contribution 2. That also operates in a very similar manner, except we use 2 bounces to collect the information. It's using stochastic next event estimation to pull data from whatever lights are in the scene. And it's expensive, and it needs this stochastic process to kind of keep track of the expense of the algorithm. In terms of improvements, these are fairly significant in 423. Specifically, the sampling pattern that we use was completely redone. So we we were using a fairly naive procedural Halton sequence that's been replaced with this significantly faster amalgam of Halton and blue noise that's fairly constant cost and is no longer ALU bound. It just uses a couple of texture fetches. We also decouple in the skylight pass, we decoupled this sample generation from ray generation, which is also very powerful because we basically leverage the property of the tile blue noise sequence to generate a very small subset of candidate sample patterns to then represent ray directions, and gave us about a 2x speed up from the previous work. And finally, the denoising, especially in GI, is greatly improved. Like significantly more improved than in 422. It looks really good. To speak just briefly about path tracing, this is unchanged from 422. The motivations are still that it's meant to be a reference and something to compare against ground truth. It's meant to be unbiased and the foundation for other techniques. This is the foundation for which the GI pass was developed, for instance. It has not gotten much different from 422. I'll talk a little bit about a few examples of using ray tracing in our engine. So the first example is using image-based lighting. And so in this example, we're using the skylight pass in conjunction with global illumination. And the HDRI sequence at the bottom is the input to the skylight. So it's using that hierarchical sample warping algorithm that I spoke about to find the sun and manipulate rays to its direction to resolve the noise. It's also important to note that this is interactive, but it's not real time. So we're hoping that additional advancements in sampling, like the one that I discussed earlier, and advancements in denoising specifically for this pass will bring it to real time. This was a data set provided by Quixel and rendered by our artists Joji and Marion and Epic. I'll talk a little bit about ray tracing in Fortnite, in the cinematics specifically, and I have a few breakdown images to show. So these are a bunch of candidate loading screens that we have for Fortnite. And as Juan said, the team has gravitated towards using ray tracing to get secondary effects. So this is the base rasterization image. This is the image with ray traced shadows. Go back and forth a bit so you can see the differences. And this is with ray traced reflection. You can see that we're getting light now that was previously occluded from SSR, especially on the vehicle on the left, and some specular changes on the right because the view direction is technically different between SSR and RTR. And then here's the difference with the global illumination pass. So it just brightens up the ambient. It also adds some detail there under the building where you didn't see before. So it's pretty nice. And here's a second example, again, completely rasterization-based pipeline. And rasterization, but with ray trace shadows. Then I'll add reflection. You can see that it is strikingly different, and that's because there's a bounce card in front of the screen. And that's what's picking up the light on the weapon. And then here is the global illumination result, which really brightens the face in the foreground. Okay, so what's next? We're still in early access, and we're still working really hard to try to get to production-ready state. So that means, again, we're focusing on stability and performance. We have the preliminary multi-GPU support, and we intend to refine this. We are always looking to expand the set of geometry, and the one that Juan called out was very difficult. And we're actively working on interactive light baking and light transport techniques. And as Juan said, it's already been leaked, but Season 10 is out tomorrow, and our trailer is using all of our ray tracing technology. So please go check it out. All right, thank you very much.
Thanks a lot for